Here in example 3, what we want to do is find the area between two curves, 7 minus 2x squared and y equals x squared plus 4. So obviously in order to do this, we need to graph them. So I'll pause this real quick, practice graphing it, try to draw it yourself, and then we'll come back and look at the graph together. Okay, well here on the left, I went ahead and drew the graph. And it looks like I've got the purple line representing the x squared plus 4 and the green line representing the 7 minus 2x squared. And so obviously we're going to find the area between. It's just going to be this little segment right in here. Okay, so to find the area, it's going to be, looks like where they intersect, where they start, is going to be at -1. So integral from -1 to 1 of the upper curve, the green one, so 7 minus 2x squared, minus the lower one, which is x squared plus 4, and then dx, since x is our variable in both equations. Okay, let's clean this up though first before we go through to take the integral. So -1 to 1. Let's see, a -2x squared plus 1 would be a -x squared. 7 minus 4 is plus 3. And then that dx. And you know your brain's getting tired when you decide that -2 and a -1 is going the opposite direction. How about this? -3x squared. My goodness, need to make sure I catch my work. So -2 minus 1 and 7 minus 4. Okay, now let's go about taking integration. So -3, and the integral of x squared would be x cubed over 3. And then the integral of 3 is just 3x. And then together, both of those need to be evaluated from -1 to 1. Okay, or looking at it, if I just kind of reduce that just a little bit, -x cubed plus 3x evaluated from -1 to 1. Okay, so let's plug in the upper bounds. It's going to be a -1 cubed plus 3 times 1, which is 3, minus the lower bound plugged in. So -1 cubed plus 3 times -1. Okay, and we'll get a final answer then, 4. And it looks like that'll be a 2 right there in the front. Let's see, a -1, so 1 minus 3, so 2 minus that looks like an overall area of 4. And there's our answer. Okay, so example 4. We want to find the area between these two curves. So let's break them up. We have both quadratics. One's going to be y squared is equal to x, and the other one is y squared is equal to, let's see, make sure I do this right, 3 minus x over 2. Okay, and if we want to take 2 seconds, obviously the first thing we need to do is look at the graph so we can decide how on earth we're going to be doing this. And it looks like because they're both y squareds and y squareds, we're looking at parabolas opening this one. Since x is positive, we're going to be opening up to the right. And this one, since the x is negative, will be opening up to the left. So I'll pause it real quick. Let's both take turns to graph this. If nothing else, you can just do a t-chart. Where this time, what I would do is pick maybe your y values, maybe your x values, but yeah, just do a t-chart and then get some values and let's specifically focus on those intersection points. Okay, well, hopefully y'all are pretty much getting the exact same thing that I've gotten. And so we want to figure out the area between all this. Okay, I'm going to show you guys something. So we're going to do a little bit something different. Obviously, I don't want to do the upper curve minus the lower curve because for part of it, it would just be purple line to purple line and green line to green line. So what we're going to do is we can also alternate this. Instead of going from upper to lower, where upper being your positive and lower is being more your negative, we can go from right to left, okay? So it's almost like you're looking at it going this direction, okay? Where the right curve would be the green one, and then the left curve would be the purple one. So we can do the area now as instead, and I'm going to come back here for these integrations, the numbers from what to what in just a second. But we're going to do the right one, and this time's because I'm going from along the x-axis, I need these equations solved for x. So this one right here would be x is equal to 3 minus 2y squared. So I'm going to focus on that one, and this one's already x equals y squared. Okay, so my right one, which is my green one, is going to be, what I'm going to plug in is 3 minus 2y squared. And now I'm going to subtract my left one, which is my purple one, which is y squared. Okay? So let me come up just real quick. Let's go back to example 3 so I can make this point. Okay. When we did this one, we did the upper curve minus the lower curve. And what we were looking at is technically all these intervals that was going from the upper to the lower. See how it's going from a y value to a y value? So we had y equals 7 minus 2x squared minus y equals x squared plus 4, because we were going from upper to lower along the y-axis. Now, as I create these vertical lines start on the left side. Well, that far left side is an x value of -1. As I keep going through it, on the right side, then it's an x value of 1. So in general, when you're finding the area between two curves, if you're going from the upper limit to the lower limit, you take the y value, subtract a y value, but you run the integration from an x to an x. So on this one, we're doing the opposite. We're going to be running our area from the right to the left. So we're going from an x value, subtracting an x value. So we need to go from a lower y value to an upper y value. So this time it's going to be from -1 to 1. Okay. X value in here, x equals this, y equals that to y equals that. Okay. Now all we have to do is kind of clean this up and we can get going. So area is going to equal integration from -1 to 1 of, looks like 3 minus 3y squared. Making sure I get it right this time. And this time it's actually going to be dy's, because our variable that we have in there are our y variables. Okay. Well, let's break this up. So the integral of 3 is just going to be 3y evaluated from -1 to 1 minus 3 times y cubed over 3 evaluated from -1 to 1. Okay, or 3y from -1 to 1 minus y cubed from -1 to 1. Okay, so my area is going to be 3 times the top minus the lower minus the top minus the lower. Okay, and I'll get an answer. Let's see, 1 plus 1 is 2 times 3 is 6. 1 cubed plus 1, so 1 plus 1. Looks like it's 2, and so we get an overall area of 4. All right, let's go on to the last couple examples. Example 5, we want to find the area between 8 cosine x and y equals secant squared x, between -pi/3 and pi/3. Okay, so we're closing down our interval for one thing. Well, let's see how this is graphed. So let's pause it, let's practice graphing yourselves, and I'll graph it with me, and then we can see what we can get, because remember, this is the best practice when you try to do some of this on your own. Okay, well, let's get started in this example. It looks like, since we have an upper curve and a lower curve, that we're obviously going to want to take the integration with respect to y values. So an upper y value minus a lower y value. And then we're going to run it from an x to an x. Okay, so the area would be a -pi/3 to a +pi/3. The upper curve with the purple one was the 8 cosine x. I'm sorry I didn't label that for you guys. This is the 8 cosine x, and this lower one was the secant squared x. Okay, and then we're going to minus the lower one, secant squared x dx. Okay, so hopefully y'all got the same thing, and hopefully that didn't mean you just put it in a graphing calculator. Just try to do it by hand. You just pick some values. So now let's go through and actually do the integration. So a is going to equal 8, and the integral of cosine is sine x, evaluated from -pi/3 to pi/3, minus the integral of secant squared x is just going to be tangent x, evaluated from -pi/3 to pi/3. Okay, so our area is 8. We're going to do the upper bound, so sine of pi/3 minus the lower bound, so sine of -pi/3 minus the tangent of the upper bound, pi/3 minus the tangent of the lower bound. Okay, so all I have to do is plug in the values. The sine of pi/3 is going to be the square root of 3/2. The sine of -pi/3 will just be the negative square root of 3 over 2, tangent of pi over 3. Well, it's just going to be that y value, the square root of 3 over 2, divided by the x value, which was 1/2. So that's going to be the square root of 3 right there. And then in quadrant 4, when we drop down to negative pi over 3, it will be a negative square root of 3. Okay, so our area is 8 times the square root of 3 minus a negative square root of 3. So square root of 3 over 2 plus the square root of 3 over 2 is going to be the square root of 3 minus a square root of 3 minus a square root of 3. So a square root of 3 plus the square root of 3 would be 2 square roots of 3. And then combining these last two results, looks like we get an area of 6 square roots of 3. All right, let's go on to our very last problem. Can you believe this? Our class is pretty much finished. We're not wrapping it up on too hard of stuff. Hopefully y'all get enough practice, but we want to find the area between sine of pi x over 2, so several multiples of pi over 2, and then y equals x. Okay, again, let's pause it, let's practice, and then we'll come right back. Okay, so drawing this final graph, we've got basically the curve, obviously, is our sine one, and then y equals x is the straight line. And so we have two equal portions. We've got one portion where the line's the upper half, and we have another portion where the curve is the upper half. And so I'm going to use basically one of those rules so we can kind of simplify this as best as possible. And obviously we're going to do an upper curve to lower curve, so we're doing integration from top to bottom along the y's. So we're going to choose x values to do our points of integration from our lower bound to our upper bound. You see how this is all symmetric? So whether I go from -1 to 0 and 0 to 1, they're both the same. So I'm going to use that property that says that when they're symmetric like that, then instead of finding the individual pieces, what we can do is just find one of them and then double it. So why don't we're going to go 2 times the area that's going to go from 0 to 1 of that upper curve, which is sine of pi x over 2, minus the lower curve, which is just x dx. Okay, and I can do that again because sine is symmetric with respect to the origin, and of course we got that line just y equals x. Nothing changing there, not another curve or anything like that. So the area then is going to be 2 times, the sine of, I've got to think about this just for a second. I'm going brain dead, y'all. Okay, the sine of pi x over 2, well, the integral of sine is a negative reciprocal of what's attached to the x, so a negative 2 over pi, and then times the cosine of that angle, which is pi x over 2. Okay, and then just the integral of x would be 1/2 x squared. All of that's going to be evaluated from 0 to 1. Okay, let's keep this up then. Let's go ahead and distribute a 2 in there just so I don't have to worry about doing it. Let's make it easier on ourselves. So negative 4 over pi, cosine of pi x over 2, and then we're going to write that as a negative x squared. So that kind of helped out just a little bit, but we're going to evaluate that from 0 to 1. Okay, let's plug in our upper bound, and then we're going to subtract our lower bound plugged in. So negative 4 over pi times the cosine of, when I plug in 1, so it'll be pi over 2 minus 1 squared. So that's the upper bound plugged into the whole entire thing. And then minus the lower bound plugged in. So negative 4 over pi cosine of basically 0 minus 0 squared. Okay. So the area will be cosine of pi over 2 is 0, so that's going to knock all of that away. So it looks like it's going to be a negative 1 plus cosine of 0 is 1, so plus 4 over pi, and then minus 0. So to wrap this up for our very, very last problem of this whole entire class, our area for this graph is just negative 1 plus 4 over pi.